Okay, let's go a little further. In the last video, we looked at how to use the periodic table to determine the number of electrons in the valence shell. So if you're in the first group of the periodic table, you have 1 electron in the outermost shell, the valence shell. If you're in the second group, you have 2 electrons in the outermost shell. If you're in group 13, you have 3. Group 14, 4. Group 15, 5 electrons in the valence shell. Group 16, 6 electrons in the outermost energy level. Group 17, 7. Group 18, 8 electrons in the valence shell. Now, one of the things that we've seen is that if we're in row 1, then the outermost shell, the outermost energy level, is 1. In group 2, it's 2. In group 3, it's 3. Group 4, it's 4. In group 5, it's 5. 6, it's 6. And 7, it's 7. And those are these integers right here, 1, 2, 3, 4, 5, 6, 7. And again, they represent the rings in the Bohr model, those shells around the atom, the principal energy levels. And those are the energy levels that electrons can transfer between when they absorb or lose energy. And when they lose energy, say they go from energy level 4 to energy level 3, then they'll give off a photon, they'll give off light. What I want to focus on now is the subdivisions of the principal energy levels. It turns out the principal energy levels, 1, 2, 3, 4, 5, 6, 7, are subdivided into what we call sublevels, S, P, D, and F. And the number of subdivisions is equal to the number of the principal energy level. So you'll notice here on this table that principal energy level 1 only has an S. In other words, there's no 1p over here. Principal energy level 2 has S and P, so there's 2S and there's 2p, but there's no 2d. Principal energy level 3 has 3S, 3p, and 3d, but no F. So what we're seeing here is that the number of subdivisions is equal to the value of the principal energy level. So if you're in energy level 1, there's only 1 subdivision, and that's called S. If you're in energy level 2, there's 2 subdivisions, that's called S and P. If you're in energy level 3, there's 3 subdivisions, that's called S, P, and D. If you're in energy level 4, there's 4 subdivisions, S, P, D, and F. Energy level 5, yes, there is a G, but we don't really see G. We don't see G in what we call ground state atoms. That is, unless the atom is excited, say by an electric field or by heat or something like that, we won't see the G. So we're really only concerned here with S, P, D, and F. Alright, now it turns out the sublevels are subdivided as well. The S sublevel is subdivided into one subdivision called an orbital, and that is represented by the blue box. So there's one orbital there. You'll notice that the S sublevel in the second energy level also only has one box, and so on as we go up. The S sublevel always only has one box. That's one orbital. Each orbital can hold 2 electrons. The P sublevel has 3 boxes, and it doesn't matter what principal energy level we're in. The P sublevel in that energy level always has 3 orbitals, which can each hold 2 electrons. The D sublevel of any principal energy level always has 5 orbitals, which can each hold 2 electrons. And the F sublevel can always hold 14. That means an S sublevel can always hold 2 electrons. A P sublevel can always hold 6. That is because each orbital can hold a maximum of 2 electrons. And the D sublevel can hold 10. And an F can hold 14. Now, if we take a look at the periodic table, we see that the first 2 rows, which kind of pop up above the body of the periodic table, those first 2 rows, they correspond to the filling of the S sublevel in a particular energy level. So in the first row, here we're filling the 1s with 1 and 2 electrons. Here we're filling the 2s with 1 and 2 electrons. Here we're filling the 3s, sodium and magnesium, with 1 and 2 electrons. Here we're filling the 4s. That is, now when I say filling, I mean that's the outermost sublevel at that point. When we're over here in the main group, in the 6 groups over here, we're filling what we would call the p sublevel. So boron has an electron in the p sublevel of the second energy level. Carbon has 2 electrons in the p sublevel of the second energy level. 3 electrons, 4, 5, 6 electrons in the p sublevel of the second energy level. Aluminum has 1 p electron. Silicon has 2. Phosphorus has 3. Notice 1, 2, 3 in the p sublevel of the third principal energy level. Sulfur has 4. Chlorine 5. Argon 6. The same is true for gallium, which has 1 electron in the p sublevel of its fourth energy level. It's in row 4. Germanium. Arsenic has 3 electrons in the p sublevel. 1, 2, 3. Selenium, bromine, krypton, and so on. So sometimes the first 2 groups are called the S block of the periodic table, and the last 6 groups are called the P block of the periodic table. Now, one of the things you'll notice is that the green part here on this table, called the transition metals, these are the transition metals, as we're moving across here, we're actually putting electrons in a D sublevel. So you see the 3D here? We're in, now, oh, look at that, we're in row 4. So that's a little discrepancy here, but remember, the row corresponds to the outermost principal energy level. Chromium has an outermost energy level of 4. Okay, it actually has an electron in its 4s sublevel. So 4 is its outermost sublevel. But what happens is we start to put electrons in the 3D, in the D sublevel of the third energy level, only after we've started opened up kind of the fourth principal energy level. Manganese has 5 electrons in the D sublevel of the third energy level. Iron has 6. Cobalt has 7. 8, 9, 10. Zinc has a full 3D sublevel. And then gallium, watch the blue box, we start to fill up the 4p sublevel, and so on. Now, what I want to point out to you now at this point is this thing up here. This is what we call the electron configuration of this element, gallium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. That is a way to write out where all the electrons are in the atom in terms of energy level and sublevel. You'll notice that all the s's can hold 2. That's because we're looking at these right here. All the s's have only 1 blue box. Each blue box can hold 2. All the p sublevels can hold 6. That's because each p sublevel has 3 blue boxes, and each blue box can hold 2. And the d sublevel can hold 10 because there's 5 blue boxes, which correspond to 5 orbitals, and each orbital can hold 2 electrons. If we start with hydrogen, let's go back to the beginning, we see that its configuration is 1s1. If we go to helium, it's 1s2. Lithium, 1s2, and then 2s1. Look at these little blue boxes here. 1s2. What does the 2 stand for here? 1s2. The 2 stands for the fact that there's 2 electrons in that sublevel. And the 1 next to the 2s stands for 1 electron in the 2s sublevel. Beryllium, 1s2, 2s2. Surprise, surprise, we have 4 electrons. Here they are. There's 2 in the 1s, 2 in the 2s. 1s2, 2s2. So this is not a squared term here. We're not squaring anything. This is just telling us that that's how many electrons there are in that sublevel of that principal energy level. Let's just jump ahead here. Nitrogen, 1s2, 2s2, 2p3. What does that mean? It means there's 2 electrons in the 1s orbital. There's 2 electrons in the 2s orbital. There's 1 electron in each of the 2p orbitals. There's 3 orbitals in the 2p. Remember, there's 3 subdivisions in a p sublevel. Oxygen has 2p4 as its outer sublevel. Fluorine, 2p5. Neon, 2p6. I want you to notice something here. What's our outermost energy level here? What's our valence shell? It's shell 2, energy level 2. Look how many there are. 2 and 6. That equals 8. We're neon. Look at argon. 2 and 6. That equals 8. Look at krypton. 2, 4s2, and 6, 4p6. Notice how I skipped over the 3d10. Why? Because that's not the outermost shell. 3 is not the outermost shell right here. 4 is. We're looking for the highest integer here. So when you're writing electron configurations, you're writing these symbols right here. You're writing the 1s2, 2s2. Basically what you're doing is you're listing. You're telling me how many electrons are in each sublevel of this atom. That's what we're doing. That's called writing an electron configuration, and you can do it based on the periodic table to a large extent. Now you got to be a little careful when you get down here. After you get to barium, you go to number 57, lanthanum, and what happens is the table is split so that, or it's condensed, I guess, compressed. They don't want the table to be too long, so what they do is they take these two rows here, these two rows at the bottom, and they pull them out of the table and drop them down. But they really should be squeezed in here. So in other words, after you get to number 56, barium, which ends in 6s2, you go to lanthanum, which ends in, let's see here, lanthanum should have one more, and it's 5d1. Now they pull it out here because lanthanum is actually an exception. According to this diagram, we would expect lanthanum to be 6f1 before the 5d, or I'm sorry, 4f1. And when we look at cerium, that's actually what we see, 4f1, 5d1. So there are some kind of exceptions to the filling rules here, but what I want to point out at this point is the block that's down here, called the rare earth elements or the rare earth metals. Those are filling the F sublevel of either the 4th or the 5th principal energy level. And as you click through here, you might see some weird things happening, and those are exception to the filling rules that we will talk about at another time, possibly.